Ash, it is really happy to invite you to the next class. We have discussed about this discrete mathematics already, titled Recurrence Relation. Two examples we have taken. The first one is arithmetic progression, where each element is increased by the common difference from the initial element, and this is the recurrence relations, and the solution is nothing but the terms which satisfy the recurrence relation is called the solution of this recurrence relation. Examples I have given: 5, 8, 11, where the initial element is 5. The next successive elements are obtained from the previous elements by adding the common difference 3. And another discussion was on geometric progression, where first element is A, the remaining elements are coming by multiplying the common ratio R. A, AR, AR square, AR cube, like that. So solution is nothing but the terms which satisfies this recurrence relation is called the solution. That's also I was discussing. Here the first element is A, the common ratio is 3. 1 into 3, 3, 3 into 3, 9, 9 into 3, 27, like that it will go on. This is a good example for the geometric progression. Now definition comes. So after understanding the two above special type of sequence of numbers, one is arithmetic progression, another one is geometric progression, where the successive elements are coming from its previous elements, we come to the definition of the recurrence relation. Definition of the recurrence relation. A recursion relation is nothing but the sequence an in which each an can be obtained from one or more of its previous steps. That's what we were discussing previously. Of the sequence a naught, a1, an minus 1 for all the integers n with n is greater than or equal to n naught. N naught is the initial element. So a recursion relation is a relation which is connected to a sequence such that the next successive elements, take for example a1, a2, a3, are obtained from its previous terms, one or more previous terms. Now what is a solution? We were discussing just before that a sequence which satisfy the recurrence relation is called the solution of the recurrence relation we discussed before. Now look at this. It's another example for the recurrence relation. An equals to an minus 1 minus an minus 2 for n is greater than or equal to 2, where an equals 5 for all non-negative integer n. So for all n the answer is 5. The answer is 5. Even though we have this definition, but this solution says each element here will be a 5, 5, 5, 5, like that, because if you put for n is greater than or equal to 2, then what we'll have here, suppose a is equal to 3, we'll have 2 into a 3 minus 1, that is 2 minus a n minus 2, you will get the 0 here, but here a 3 minus 1, 2 you will have, but a2 equals 5. So here a3 is equal to 5. So you will have the sequence as 5, 5, 5, dot dot dot. So this is a good example for recurrence relation for which this is the solution, or this is a solution. These terms are solution for these recurrence relations. Now coming to understand this concept of recurrence relation and the solution, let us come to the understanding of the real life situation. Okay, so remember that what is a recurrence relation? A recurrence relation is one in which the successive terms can be obtained one or two or more of its previous terms. Then it is called a recurrence relation. Now we have to prove that compound interest is a recurrence relation. Compound interest is a recurrence relation. That's what we have to prove here. Now look at that. Let P denote the amount in the account after n years. We are depositing some amount in the bank. Now P denotes the amount in the account after n years, the total amount after n years. Since the amount in the account after n years equals the amount in the account n minus 1 years plus interest for the next year, we see that the sequence P1 will satisfy the recurrence relation. This am I correct? Pn, the next year amount would be equal to the previous year's amount plus or times the previous amount. This is what? The interest amount, the total amount. So that amount plus, after adding what we have, that amount, interest on this amount, add these two, what you will get? The total amount of that particular year, the nth year. So nth year total amount would be equal to the previous year plus the interest of the previous year for that particular amount. So simplify this, you will get 1 plus r into Pn minus 1. Common factor is Pn minus 1. You bring it out, 1 plus r to Pn minus 1. Look at this particular equation. This equation is an equation or where the successive terms, the total amount is based on the previous amount multiplied by this 1 plus r. So this is, we call it as a recurrence relation. Am I correct? So this Pn satisfies this recurrence relation. Therefore this would be the solution for the recurrence relation 1 plus r to Pn minus 1, that equals Pn. So set of all this Pn, P1, P2, P3, P4 will give you the total amount in the first year, in the second year, in the third year. That is a sequence, a recurrence sequence comes from this particular recurrence relation. Pn equals 1 plus r into Pn minus 1. So we have to note that Pn can be obtained from its previous terms here. Recall the recurrence relation definition. If a sequence is such that there exists a recurrence relation such that each terms in the sequence, successive terms I'm talking about, comes from its previous terms, then we say that it is a recurrence relation. So this is a recurrence relation connected to the compound interest. So this we call it as a compound interest. At the nth year we have 1 plus r, where r is the rate of interest, to Pn minus 1 will give you the total amount in the nth year. Okay, so for different n you will have different value, and n denotes the number of years. So we must prove that compound interest is a recurrence relation which makes this sequence. Now we are applying this particular idea of recurrence relation connected to compound interest, okay, to solve a problem, a particular problem. We are going to solve that now by using the previous compound interest recurrence relations. Pn equals 1 plus r to Pn minus 1. Now let us discuss this wonderful problem. Suppose that a person deposits $10,000 in a saving account at a bank which yields 11% per year with interest compounded annually. How much will be in the account after 30 years? Wonderful problem. You make a racket. Now what's the problem? Deposited amount $10,000. How much interest by the bank? 11% per year, compound annually. How much will be in the account after 30 years? After 30 years, what would be the total amount in its account for depositing 10,000 at the rate of 11% per year compound interest. We know already about the compound interest recurrence formula. Pn equals 1 plus r Pn minus 1. Now what is interest given here is 11%. So 11% means 0.11. 1 plus 0.11 into Pn minus 1, the amount in the previous year. This is amount in the nth year. Now let us have what is the amount in the first year. The amount in the first year would be equal to we are adding here, we get 1.11 and 1.11. This year P1 after 1 year, P0, that is the initial amount, P0 into 1.11. The second year total amount equals 1.11 into its previous amount P1. So P1 already we know that it equals 1.11 P0. Therefore in the place of P1 we can substitute this to get 1.11 into 1.11 into P0. Now what would be the P3? This third total amount in the bank equals, by this particular formula, P3 equals 1.11 to P2. 1.11 multiplied by the second deposited amount. So here P2 equals 1.11 whole square into P0. So 1.11 into 1.11 square into P0. In the place of P2 we are substituting this, we get this. If we go like that, then Pn would be equal to, if you see there, if 1 comes here, then 1.1 to the power n into P0. P2 comes here, 1.11 squared into P0. P3 comes here, 1.11 cube P0. If we go like this, we will have Pn equals 1.11 to the power n into P0. Okay, so Pn, the nth year. Now in the question what they ask is that what is the total amount at the end of 30 years? That's what they ask. So applying that formula, put n equals 30, we will get 1.11 to the power 30 into 10,000. 10,000 is the amount deposited at the beginning. Look at that, the dollar, $10,000 given deposited amount. So 1.1 to the power 30 into 10,000, given P0 is equal to 10,000. Therefore this, calculate this, find out that would be the amount in the bank after 30 years if the interest is 11% per year and the initial deposited amount is 10,000. So this way we can solve the compound interest formula by using a recurrence formula. By using this recurrence formula, it is possible to use that. Now some other general formula here comes. Let A and B the sequence that satisfies the recurrence relation. An equals an minus 1 minus an minus 2. The difference between n minus 1 and minus 2. The difference between its previous elements and its previous elements. The difference of them is an. That's what the recurrence relation says. For n is equal to 2, 3, 4 dot dot dot. For n is equal to 2, 3, 4 dot dot dot. The recurrence relation is given like this, which gives a sequence like this, or this sequence satisfies this recurrence relations for n is equal to 2, 3, 4. Okay, right. Now we are supposing that a0 equals 3 and a1 equals 5, because without these two initial values it is impossible to calculate the question a2 and a3. Am I correct? So for example, you take here a2, then you should have here a1 minus a0 you should have, then only you can get the value of a2. a3 also, a3 is equal to a2 minus a1 you should have, otherwise we cannot get the answer. So the initial values are given to us. Now look at the problem. We will find out what is the value of a2 and a3, a2 and a3. Given the recurrence relation is an equals an minus 1 minus an minus 2. An equals an minus 1 minus an minus 2. Now we have to find out this a2. So a2 would be equal to a2 minus 1, that is a1, minus a2 minus 2, 0. So a1 minus a0. But the initial value given a0 is equal to 3 and a1 is equal to 5. Therefore a1 is equal to 5, a0 is equal to 3. 5 minus 3 equals 2. Now the next terms that they are asked in this particular sequence is a3. What would be a3? So a3 would be equal to, from this particular formula, a3 is equal to a2 minus 1 minus a3 is equal to a3 minus 1 minus a3 minus 2. That would be a3 is equal to a2 minus a1. We already found out that a2 is equal to 2. A is equal to 2. Therefore a2 minus a1, we have the value as 5 here. Therefore 2 minus 5 equals minus 3. So for this sequence, a1, a0 is 3, a1 is 5, and a2 is 2, and a3 equals minus 3. So that's what one of the simple problem. Now next problem is about where we have to check whether the sequence an is a solution for this recurrence relation or not. The sequence is called the solution of this recurrence relations if each term should satisfy this particular recurrence relation. If each term of this particular sequence should satisfy this recurrence relation, okay, then only we say that this sequence is a solution for this recurrence relation. Now we have to check whether an equals 3n. This is one of the solution formula. For different n you will have different value, that is satisfying this recurrence relation. Not we have to check whether this is a solution set for this recurrence relation. That is what we have to check. And last problem, an equals 2 power n, whether that satisfies this recurrence relation or not. That is what we have to check up. Now let us have this problem by taking an equals 3n. The first question, an equals 3n, whether this is a solution for this recurrence relation or not. If this is a solution, this a1, a2, a3 should satisfy this particular recurrence relation. An equals 3n should satisfy this recurrence relation. Let us check that. Now for n greater than or equal to 2, we see that 2an minus 1 minus an minus 2. Okay, now we are taking this 2an minus 1 minus an minus 2 can be written as 2 into 3 times n minus 1 minus 3 into n minus 2. Why? Because an is equal to 3n. In the place of an we are substituting 3n. If here n minus 1 comes, then we have to write 3 into n minus 1. Suppose here n minus 2 comes, 3 into n minus 2 we have to write. So this is the formula 2 into an minus 1. So an minus 1 is equal to 3 into n minus 1 minus an minus 2. An minus 2 would be equal to 3 into n minus 2. Am I correct? An is equal to 3n. Therefore, an minus 2, that is an minus 2 would be equal to 3 times n minus 2. That is what we have here. Okay, you simplify this, you will get 3n, and that 3n is what? That 3n is what we have here, 3n. So an, that's what here, an, which equals 2an minus 1 minus 3n minus 2 equals 3n. So in this particular formula, this an satisfies the condition. An satisfies the condition because if you substitute this value in this equation, at last we have an equals 3n. That's what we see here. So an equals 3 comes when we substitute this value in this regression equation. Therefore, this satisfies the regression equation. Therefore, this is a solution for the regressions relation an equals to an minus 1 minus an minus 2. Now let us take this an equals 5 is a constant one. Okay, whether this is a solution for this or not, we will check up. Right, now let us take that one. Suppose that that's the next problem, I think. Now take this one. Yes, afterwards will come there. An equals 5 for all non-negative integer n. So for n is greater than or equal to 2, now we are taking the regressions, given regressions relation, regressions relations here, and check an equals 2 into an minus 1 minus an minus 2. So this an is a constant for whatever it n may be n minus 1, n minus 2, n minus 3, whatever may be n, the value is 5. So an equals 2 into 5 minus an minus 2 is also 5, therefore 5. So 2 into 5, 10 minus 5 equals 5. Okay, so what we have see here is that an equals 5. An equals 5. That an equal to 5. An equals 5. So this regression equation satisfies, or this formula of n formula satisfies this regression relation. Therefore, this is a solution set for this regression equation. This is a solution set or solution for this regressions relations. Now what's the last problem here we have to check is that whether an equals 2 power n is a solution for this particular regressions relation or not. That's what we have to check now. Now let us take that one. Now suppose that an equals 2 power n. Now take the particular equation here. An equals 2an minus 1 minus an minus 2. That's what the given regression relations. Am I correct? This is the regression relations. Now for a naught, what will have? 2 to the power 0 I will have 1. For a1, what will have? 2 to the power 1, 2. For a is equal to 2, what will have? 2 to the power 2, 4. So a0 we have 1, a2 we have 2, a2 we have 4. Now this is the regression relation. So let us have for the second term a2, we have to get 4. Whether we are getting 4 or not, we'll check up. When a is equal to 2, we have 2 into a into 1, because 2 minus 1, a1 minus a naught, and 2 minus 2 a naught. Right, from these calculations, 2 into a1 equals a1 equals 2 into a1, that is 2 into 2, 4, minus a naught is 1, so 1, so 4 minus 1, 3. But a2 is equal to 3 comes, but that here a2 is equal to 4 comes. Here when I put in this particular equation, the second term I am getting is 3, but according to our own calculation, second term is 4. Therefore a2 is not equal to this a2. Therefore definitely this will not be a solution to this equation, because this equation called regression equation is not satisfied by this solution formula. Here 3 comes, but here 4 comes, so not equal. Therefore this solution not satisfying this regression equation. Therefore this sequence will never be a solution for this regression relation. So going back, this is solution to this regressions relation. This is a solution to this regressions relation, but this is not a solution to this regression equations. Okay, so with that we come to the end of this problem, and the next class we talk about the rabbits and the Fibonacci numbers. Fibonacci numbers, very important for the examination point of view. We'll see this later. Thank you.